from OVARP and David Marks and Julia Barfield, who have their own architectural practice. Jane is also visiting professor at Harvard in the Graduate School of Design this year. So it's quite hard actually getting everybody to be free on the same night for this talk. These three people have a history of working together, I think over a decade, 10 years or so, and there's a number of projects that they'll talk about tonight, but focusing on some particular projects like the Millennium Wheel project and the Bridge for the Future, to just sort of illustrate the collaborative process that they go through and what the disciplines and the different people bring to that process, which I think is the interesting thing about having all three of them here tonight. Some of the issues that they will be discussing is the title is actually An Arch Never Sleeps, which I think is a private joke, which perhaps Jane or someone will explain tonight. Moral principles, geometry and public participation are also some of the themes that they'll be discussing. So I think you're talking together, is that correct? But Jane's controlling the buttons on the slides. Okay, so if I hand it over to Jane, David and Julia, thanks.
Hello. I thought I'd start actually talking a little bit about myself and how I got into this collaboration with David and Julia. I started working with Arabs really decades ago, before I went to university, and had quickly after graduating started to become aware of what Ove had been talking about. There's a speech that he addressed to the firm called the Key Speech in the 60s, which set out some of the principles that have really been my inspiration, I suppose. He not only talked about engineering, but in the speech he was really talking about the nature of the firm and the idea of a company which is a place where people can grow and explore ideas. And also what I think was quite unusual, perhaps it's very unique for it to be expressed, was that he put moral principles on the agenda. And he didn't try to say what the firm's principles should be, but he said that it's right to use moral principles as the bedrock of what you do. And that, to me, is very important. It means that I feel that it's quite all right for me to decide what I should do, and that not only will I not be harmed if I do that, but I'll be encouraged to. The other thing that was unusual about him was that he and his partners in the 70s actually gave the firm away. It was a partnership, and they decided to make it a firm where there was no ownership at all. So when partners retire, they don't take anything with them apart from a pension. And I think that's quite important. It means that we can't be bought by other people. If you're a public company, then the shareholders really expect to have something in return for investing money in what you're doing. And if they perceive that what you're doing is not profitable, they can try and tell you what to do. And I hope that we can always hold on to those two aspects of the company. I wouldn't stay if they didn't. The other person who had a big effect on me, of course, was Peter Rice. I was lucky to work with him quite early on. And he was somebody who encouraged young people in particular. Always kind of said, it's actually, knowledge can be really dangerous. It can freeze your mind so that you stop thinking about things. I was working on a project with Foster, the BBC radio headquarters, when I was in my late 20s, and that's when I met Julia, and Julia asked me if I'd work with them on the Grand Buildings competition, and that was the first time that I really collaborated with any architect on my own as opposed to being a cog in a huge team. And it was an enjoyable experience, involved lots of breakfast with almond croissant. And I've been in touch with them ever since. I shortly after, in fact, went to Los Angeles. In that office, we were working on a wide range of projects, a lot of them institutional laboratories and hospitals and things like that. But if I could have the first two slides. One day I got a fax from Julia saying there's another competition we'd like to talk to you about, and it was this competition for a bridge competition that was set up by the Institution of Civil Engineers it was a bridge to be an image of the future. And I'd like to let David and Julia start talking as well now. and hopefully we can tell you a bit about how we have worked over the years and how our ideas have developed.
Well, it was an irresistible competition because it was, the title, The Bridge of the Future, was quite irresistible. And then the idea of actually designing a bridge related to nature was part of the brief. So that got us to thinking about how nature would design a bridge. And we got talking about the structure of a horse, and then that led us on to the structure of a dinosaur, and that became the inspiration for the bridge. On the right-hand side, you can see the nature tends to design very efficiently and very beautifully. That's a vulture's wing in the form of a warren truss, and this is the skeleton of a dinosaur, which became the inspiration for the bridge.
We talked quite a lot about what we wanted the nature of the bridge to be like, how you'd experience it as you walked across it, and the idea of the suspension bridges that you see in the desert or something. You just walk along and they kind of move as you go along it. And since this was a pedestrian bridge, there's no reason why it should be really, really rigid.
Engineers are generally taught to design movement out of a bridge, and we decided that it would actually be, the experience of actually walking along a safe but movable bridge would actually be something that we were after.
So we started kind of faxing what we thought we were talking about back and forth. And
strange hours in the morning and the night.
Yes, exactly. The 8-hour time difference was quite helpful. Kind of got onto this idea of it would be a bridge that would be anchored on one side, and so have vertical and horizontal support on one side, the right-hand side on this slide, and at the other end it would be kind of supported by almost a ball bearing that could roll around, and start to explore what the nature of the structure needed to be. And we had in mind, the quadrupedal bridge that Darcy Thompson talked about in Growth and Form, of the vertebrae carrying the compression and the tendons modifying the deflections, but not actually stopping movement. And those slides just show what connections between the vertebrae need to be, whether it needs to be moment connections between it, which is the slide on the right. If you didn't have any cross bracing at all, then you'd need to try and get moment connections at those points. And then I got the slide on the right, shows the facts from David and Julia saying, well, could all the bracing come from one side, and what would happen what's the walkway like? How should it be supported? And so we developed that idea with all the ties coming from one side and going for the moment connection between the vertebrae. And these slides show the development of the idea of the vertebrae. So the one on the right was my doodle, and then David and Julia made the model on the left.
We made the model at the same time, sort of on the other side of the Atlantic. It's an upside-down model.
Yeah, and well, for the entry, we had to actually decide where this bridge was. Up till then, we've been really sort of just talking about an idea of a bridge in the abstract. So decided to put it over the Grand Canyon, since that was in between us at the time.
We won the competition, by the way.
And then, so yes, after that success, well, when I came back from LA, there was another competition this was for bridges to replace the covered timber bridges in Vermont, and the idea was to have a whole series of bridges, different spans, but all the same idea. And we wanted to look at using timber, but in a more modern way.
And also the idea of using the deck in composite with the structure below, so that you get actually a very thin deck.
So in fact, what the deck is actually, it's reinforced concrete, a thin 6 inches of reinforced concrete on top of timber beams that are all laid on end, and you get composite construction by having shear connectors between them, and then just having the tie underneath to increase the lever arm, that part there. So that made the deck just needed to be deep enough to span between the edge and the midpoint of the deck. And on the right-hand side, you can see that the casting that we wanted for the pin supports. It's a tied arch, with zigzag hangers.
This was the first arch that never slept.
It actually was a competition where we had to submit the calculations with the entry, which is a bit unusual. We then did another competition, which in fact was successful in terms that we won the competition. It didn't actually get built. Spayhawk had its competition for a local centre for Thames Valley Park near Reading.
This was a 200-acre business park that they were developing at the time, and 100 acres of it was going to be a natural park, and the other 100 acres was going to be a large amount of office space. But this was the local centre that consisted of a 150-bed hotel, something called the Information Age Centre, which was an exhibition centre which was sponsored by people like the Science Museum and various members of the IT industries to display their wares. It was actually going to be an extension of the Science Museum, and it was designed for children from 7 to 19, and it was trying to get more people into the IT industries, and that was linked to a conference centre and a leisure retail building. And what we did was we actually positioned the buildings in such a way that they formed the square, which would become the heart of this business park.
We also arranged it so that the buildings are pretty well coming up to the edge of the usable land, which was along that line, because all this area here, the river meadows, which flood occasionally, and took advantage of that to bring the water up into this area.
And then we used the water to heat and cool the buildings. It was with heat pump system.
So, the slide on the left shows the beginning of the ideas for the structure. These buildings here have 34-metre clear span, and the columns in this direction at 14-metre centres. And we wanted to have a structure that would look quite light and be expressive. It's basically primary curved trusses along these lines that then support these gull wings, which have a strut on top here, so that they're bending stiff, and there's a pin here between them. Because of this kind of arch shape between the trusses, that actually gave lateral stability to the primary trusses, which was quite handy. And then just a couple of places down each side, we just put cross bracing between the columns.
This was our flight of birds. Then we were invited to Liverpool by the Merseyside Development Corporation for a limited competition to look at the Pier Head site, which is, as everyone probably knows, it's the primary public area in Liverpool. And if you go to the next slide.
Sorry.
We'd never actually worked in Liverpool before, so we first of all did quite a lot of research into the development of Liverpool, and this shows one of the panels that we presented, and it enabled us to understand about the growth of Liverpool. And this is just an example of sort of an approach to site and site context. So, moving from the 17th century down to the present day, we analysed it in terms of the city growth, what happened to the waterline, and what happened to the public realm, the public spaces. And I mean, the story it tells is absolutely incredible, really, when you see what happened in the mid-19th century through to... actually, this doesn't work.
Battery's gone.
Battery's gone. Oh, right, here we go. Back again. Yes, I mean, all the docks were were all built in the water. I mean, the expression of confidence that this showed is incredible. And then these show the sort of links between the water and the sort of cultural heart of Liverpool, and how this was broken and is broken now. And part of the project was to sort of retie the waterfront to the heart of Liverpool, which is broken by a 7-lane highway at the moment. And this was another part of the site analysis, which showed comparative sizes of various public spaces. This was Venice, that was Beaubourg, and that was Red Square, which was quite incredible. We actually discovered that Pierhead was about the same size as Red Square, which was a bit of a surprise to us. I mean, the brief was basically there was two strands to the brief, one of which was to design a landscape plan, a £3 million landscape plan for Pierhead that could be carried out in the short term. And they also asked for sort of a vision for the future. And this sort of incorporates the two of them. And one of the things that we proposed was that this 6-lane highway be put underground, for the sort of long-term plan, so that area could become a park. It's gone again. Anyway, the area between the Three Sisters buildings and the central town could become a park, and actually, that would make this link between the Mersey and the centre of town. The other thing we did was we talked to Tom Lawson of Bristol University about the space, because it's a very hostile space. I mean, it's very dramatic and it's a wonderful space, but it's also quite hostile, very, very windy. People have been known to have to hang on to lampposts in order to stand up in certain wind conditions. So we talked to Tom Lawson, who's an expert on wind, and talked about where we might position various buildings to temper the environment. And the conclusion was that this winter garden, which we proposed along the parallel to the Mersey, would actually create a sheltered walkway along the Mersey, which is something that the MDC is promoting all the way to Albert Dock, which is sort of that way, to Princess Dock, which is that way. And also, it would also help the environment in the main space as well. So maybe you'd like to talk about the winter garden.
So the winter garden was quite a nice sort of building to put there, because it would be transparent and you'd be able to see through it. And we decided to come up with this particular structure, which is it's really like a single layer membrane structure that forms these saddle shapes between these arches. So the arches are made of trusses, and the saddles it's actually a cable net. And the thing about a membrane structure is that you need it to have curvature in two directions, so that if you apply downward loads on that curve, for example, it's that cable that can take the load. And if you've got upward loads due to wind, that there's a curve in the other direction, which acts as an arch that can take that load. And also, it's a structure which basically has triangulation in plan. If you go from the ground and to find a cable that goes up, it then hits an arch. So you do get triangulation for loads in this direction, which you can rely on if you're using cables, but you wouldn't be able to if you were using fabric, because you have to, with the fabric structure, you always have to think of the situation of what happens when there isn't any fabric there. And then across in this direction, the arch itself is quite stable.
We also developed a system of natural ventilation for the winter gardens with our services engineer Lauren Butt, and we talked to glass manufacturers, didn't we? We talked to Pilkingtons, who actually who are actually being reasonably helpful on this project. Yes, they didn't throw up their hands.
Perhaps they didn't think we would win. Well, this is another competition, Venice Gateway competition.
Yes, I mean, we'll describe this very quickly. Yeah. This was, everyone probably knows, but where it's the Piazzale Roma, and the proposal was for a gateway which along the canal, and also it was redesigning the coach station. maybe you go to the next one, we can describe the structure.
Yeah, we'll just touch on this quickly. So the was looking at these panels which are folded plates, which really just act as, this is like a 3-pinned arch. So this plate has some bending stiffness because it's folded and goes up to the top of that column, and the column goes down to the ground. And each of these plates actually touches each other so that they lean against each other in that direction. And we were using timber, and the references were to the hulls of the gondolas, the boats.
And sort of Gothic arches.
Yeah. Now, so that all of those competitions and things, I suppose, were really the kind of the foundation of our conversations. We're kind of just dipping in and out of conversations a lot. But then finally we got to a project which we got to build.
Yes, first built project. We were invited back to Liverpool by Merseyside Development Corporation to design a water sports centre, which was going to be in Queen's Dock, which is there. So it's all the way along from sort of Pierhead there. And there was actually an existing water sports centre that was housed in porter cabins and things like that. A very successful one, which was mainly for sort of kids in Liverpool to learn how to sail and windsurf and canoe. And what they did was that they gave hour-long courses, which meant that it was accessible, so they were cheap and therefore accessible to a very wide range of people. And we kind of sort of continued the historical research, and we discovered, we looked at the sort of traditional buildings that had been built around the docks, and this was one that we discovered, which was cast iron columns with timber infill. And that on the right is actually a picture of Queen's Dock, only in 1948, which is, the dock actually declined very, very quickly.
So we knew we had this site which was basically, a bit of water that you had to get to by
That's
a
right.
bridge.
The client gave us a site which was in the water, and he gave us a budget, and that was all he gave.
And the budget was about £1 million, so quite small. And so we started off looking at ways of putting a building on the water. That's just what the slide on the left is. I mean, the water level doesn't vary by very much, but by about 300 millimetres.
Plus and minus 3.
Yeah. And in some ways it would have been very nice to have a floating structure. We actually did some research on making a sort of barge structure, or even trying to buy an old barge. That turned out to be the most expensive option. It would have blown half our budget, so it was just out of the question. Which is why we really ended up with, the option that you can see number 5 on the right, this combination, basically piles that go down to the bedrock. So they're about 13 metres long, and they support a deck that's just above the water level, and then we'd have floating pontoons around the edge.
They would take up
They would go up and down, so that they would have a ramp bit so you could get up to the level. And you get to this building by bridges, of course, off the dock wall, which is what the slide on the left shows.
So yes, basically the brief was for showers. There was a very clear component of wet facilities, which was showers, staff facilities, storage of wetsuits and things like that. And then there was the clear division between what was the sort of the dry component, which were the offices. They wanted a lecture theatre and a cafe. So it was we developed this fairly simple diagram which had the wet and the dry at dock level, because another of the features of the Liverpool docks is that there's this approximately 3 metre difference between the dock level and the water level. And we used that to advantage in having the sort of main entrance to the upper level. And then you went down to the boat storage and the workshop and the plant room.
And so the slide on the right shows the structural diagrams. So starting from the deck, it was important that the columns would be set in from the edge of the deck so you can pull in the boats and windsurf boards, etc. But at the level above, we really wanted to have a clear space from side to side. So that's why these columns come up and then branch out, picking up the edge columns and also reducing the span of that slab. So each of the tops of the columns then support basically a frame which looks like it's basically a rectangular frame with a curved beam on top, which is pinned at both ends. And the bottom of that rectangular frame supports another concrete floor. So the slide on the right really shows the build-up from piles, deck, columns spreading out to pick up this frame, series of frames. And
so the building is like cantilevered 13 metres up in the air.
Yeah, from the ground.
Effectively.
Yeah.
Except that's covered in water.
And well, there's quite a light and sort of simple structure, but the one bit that we put a bit of money into, I suppose, the structural bit that we put money into was this connection between these columns, which cantilever, and the branches that they support, and we decided to see whether we could afford to have castings for that.
But it's true to say that the technology for castings has actually developed in such that it's not actually that expensive to do.
Yeah. So this is showing construction. The slide on the left is the piling rig and the water, and then we use precast concrete for the deck so that you can bring the pieces in easily, and then it had an in situ topping.
I mean, one of the reasons for keeping it that far out of the dock was that they wanted, what part of the brief was they wanted a sheltered area.
So this
to
becomes,
do, yes, for the beginners to do their sailing, and also for competitions for canoeing, so that distance between the deck was determined by that, and also security. I mean, in Liverpool, security is a
slight issue.
Big issue.
Yeah. And that's the deck finished. And you could see those boats. That was the existing centre being used. Here's the famous casting, which was Clark's of Sheffield made. Tube workers were the steel fabricators, and they used Clark's to do the castings, which is exactly the same team as we had on Stansted. And they called this casting Sputnik. And one of the things is that because you had to bring it on site and really put it together as easily as possible, we specified that they would have to do a trial erection in their works. Just make sure that that's the slide on the right, make sure that they did get the plates in at the right angle for that pin joint. And you can see on the slide on the left, you can see the shear studs here for the concrete that was going to be cast on top. It was in situ concrete for that deck. And the other thing to say about the steel is that for fire protection we used intumescent paint. And then here's slides of the finished building, showing the finished.
I mean, it's true to say that all the materials, we used quite a small palette of materials, and they were all selected because the conditions in the dock are actually salty, so it's a marine environment essentially, so quite a harsh environment too.
Yeah, and we put our kind of high paint spec, which is that you treat the bare metal first with either galvanizing or flame sprayed zinc before you start putting the layers of paint on top. Whereas if you just have a primer and put the layers of paint on top of that, then when the top paint gets chipped, you almost, you have to strip off a huge amount to make repairs to it. So this has a longer life. Even so, we would say that it has to be repainted every 8 to 10 years. Sorry.
Right. So that's the boat store on the lower level, which is quite see-through but secure. And then this was the bit that needed to be solid, was the plant room and workshop.
Well, I think a project like this, to be successful, you have to be very careful with your tender list to make sure that the people who are making the bits are people who care about it. We're very lucky to get tube workers to put in the lowest price, in a way, but we're talking sternly to them. Well, the next project that we're hoping to get into some detailed design on is this tower, which is for Bracknell Town Centre, which I'll let David introduce.
We were approached by David Robertson, client on the Information Age Centre, who called up one day and said, how would you like to build your tower in Bracknell? And,
The tower from the Thames Valley Park project.
we weren't too sure about it, but we went to Bracknell to meet Bob Angel, the leader of the council, and a couple of his council officers to talk about it. And what they were after was something to symbolize the regeneration of Bracknell. Bracknell is a new town. It was built in the 60s. It's characterized by some pretty boxy concrete architecture. And it's probably its only redeeming factor in terms of its environment, which needs a lot of regeneration, is that the center is fully pedestrianized. Oh, and it's also the home of the Met Office. So that's what Bracknell is famous for. After a lot of discussion about what they wanted, whether they wanted a clock tower or they wanted this tower that we never built at Thames Valley Park, we proposed to them a tower that would reflect both symbolically and literally the weather. And so that's how the project started. Talking to Jane, we examined a lot of different materials that would do that, and we came up with ideas for windmills and looked at wind sculptures produced by Japanese sculptors and all kinds of different ideas. And eventually we discovered dichroic glass, which is a coating that's put on glass to make it work like a beam splitter. The effect it has is to reflect the opposite color of light that it transmits. And it's a very, very pure process because unlike stained glass or tinted glass, it doesn't absorb anything. So the colors are very vibrant. And in the end, we decided to use solely that material and to put it within a stainless steel shaft, which would reach up into the sky and allow these 5-foot square sheets of glass to spin in the wind.
So we looked at options for what this mast would be like. And of course, we did start with the normal options, like 3 verticals and just having triangles connecting them on plan and bracing and everything. But to have the squares being able to rotate and be able to look at that kind of clear of clutter, it worked out much better visually to have circular hoops connecting the verticals. So this is slightly less efficient structurally, but it's because it means that you'd be putting axial forces into basically a bit of arch at 1/3 of the circle, and you put some bending in. But we found that those forces were not so big that it made that the tubes got really big. And we also looked at what the material for that mast would be, and there are a lot of elements in this mast. And if you went for mild steel and wanted to paint it, we'd be giving them a kind of huge maintenance headache. And we suspected it would be better to get them to put the money into the project at the beginning, and therefore we go for stainless steel. And again, we started talking to tube workers about the viability of that. It was also a good idea to have stainless steel because of what it would look like in terms of this reflectivity. But the other thing we had to investigate, and we'll probably need to do more studies on, is actually where the guys should go. Ideally, you wouldn't have the guys quite as vertical as this, but of course we're constrained by the buildings around. And what the guys are really doing is they're controlling the deflection of this cantilever up into the sky. And at one level you could say, well, why can't you just let it move around a lot? And you will see that there are some very skinny masts around. And that's what we need to do is the next stage, is to really determine what the deflection criteria should be. And then we can play around with what the sizes of those guy cables needs to be.
The photograph on the right is a photograph of the model, and the model makers very cunningly used actual pieces of dichroic glass, and they all span. So if you could blow on it, and they would spin, and they would do exactly what we thought it would do. So it worked very well from that point of view. And at the bottom, we're designing an interactive visitor center for kids, so they can come and learn about the weather.
And the structure of that's very simple. That's just curved beams all leaning against each other in the middle with some cladding.
What's very nice about the structure from the way we see it is that the structure is where you want it. It's on the outside, but it's a very, very open structure. It's very slender. It's although it's obviously this great big male thrusting thing into the sky, it's got a lot of feminine qualities about it as well. And we talked to Tom Lawson again about what?
What are they?
It's changeable.
I beg your pardon.
Sorry. Tom Lawson was very interesting about how the glass would react in the wind, and we learned, and we're constantly learning things about how nature works and affects structures, and the way you need to design them in response to that.
Yeah.
And I think that's relevant.
Well, this is the project we'll probably dwell on the most. It's not built yet, but we hope it will be soon. I think you should introduce this as well.
Well, the idea for the Millennium Wheel was, it's really a machine for viewing London from efficiently and safely. And it gets one up to about 500 feet. That would be the fourth highest structure in London after Canary Wharf, Post Office Tower, Canary Wharf, NatWest Tower, Post Office Tower, Millennium Wheel. But it's a very feminine structure. It's round. It's very symbolic
This
of the
bit wasn't
millennium.
planned.
Constantly turning, very slow speed. It's powered by the Thames. Doing
We will duff you up afterwards
beaten up after.
in a feminine way. I think we'll go on to the next slide.
This just compares it with some other well-known landmarks. It's big.
It's big, yeah.
It's half the size of the Eiffel Tower.
Yeah. Also, it's hanging over the river.
Well, we wondered whether there was a case for redesigning the wheel, that's probably not the right way to look at it, but looking at the way wheels were designed in the past, it became quite interesting how you would go about building a wheel this big. Not only how it would work structurally, and so you get into how the rim works and how the hub works and how everything works that needs to connect those two bits, but also how you would go about building it, and obviously looking at how other wheels were built in the past. Up until about 150 years ago, no less than that, up until about 100 years ago, the biggest wheel was the wheel on the Isle of Man, which is 72 feet in diameter, and its spokes are alternatingly compression and tension, and because it's all made out of timber, and so it has to be held together. And then there's obviously the original Ferris wheel, and the biggest wheel at the moment is a wheel that was built about 15 years ago at Cosmo World, but it's not a particularly elegant structure, and its supports are even less elegant.
I should really say that, the reason, when we first started looking at this, it was in response to the Sunday Times competition for a landmark for the Millennium, which quite a few people went in for, and nobody got any thanks, or, there were no prize winners, and there were no commendations or anything. And I was quite impressed, because David and Julia said afterwards, well, hold on a tick, we don't need this to be the winner of a competition. This can be built. It can make money for itself, and I think they were really quite innovative in just putting in a planning application for it on a site they didn't own. and I think there are lessons to be learnt here about how you can make projects for yourself. And it was at that stage when at that stage we did do some preliminary work, and in fact the first idea that Dave and Julia came to me with was just to have one half of this arm, and not to have it going all the way through.
No, well, the first idea was not to have any arm.
Not to have it. Oh yeah. The first one was a big magnet in the sky, but we'd done that one before.
We wanted it to be as visually light as possible.
Yes, exactly.
And efficient as possible.
Yeah, and exactly. And in fact, we found that this this arm was quite useful when we were thinking about how you would build it, that in a way it's a derrick. So you could build the support and then construct this arm, which would be sort of in the vertical position, and then from the river start adding bits on and rotating the arm till you get all the way around, if you can imagine that. And that idea of the stiff arm has still remained, but in slightly different form, as you'll see. But here's some more images of that original idea.
Each of the capsules, which is totally enclosed with glass, takes 16 people at a time. So there's actually about 960 people on the wheel at any one time. And it's a 20-minute flight over London, basically. It takes 20 minutes to actually go around it.
And much cheaper than buying a ticket to Paris and hoping for a clear day. So it would be accessible to a lot more people. A lot of people who never even can afford to go on a plane.
There's the only place in London that you can actually see London from a height, and as a whole, is actually at the top of St Paul's at the moment.
Yeah.
And because not everyone can actually climb all those steps.
So we worked out today that you could see the tower from the top of the wheel, the Bracknell Tower.
The other thing is we deliberately put the capsules on the outside of the rim, and they're held in these rings, and so the capsules then go round and round. And we've been looking at the bearings and things like that. Yeah, the whole capsule. So you'd always stay standing vertically, we hope.
And the other thing to say about it is that it's powered by the Thames tidal power.
Yeah.
Because it moves very slowly. Once it's going, it needs very little power to keep going.
So we probably would need to use electricity from the grid to get it started. Yeah. But once it's there, then it should just. We're hoping.
Yeah, we're going to sell the electricity back to grid from the Thames.
And we're going to cover the capsules with loads of photovoltaic cells as well. So that will provide the power for the lighting and any fans and things that we need in the capsules
To cool and heat.
Yeah. Well, recently we've actually got some money from a sponsor to do a lot more serious studies to get it to planning, and it's really an interesting process. There are, because the application went in more than a year ago, there have been lots of responses from all the people that letters are sent out to. So we've got an idea of the sort of the comments and objections that we need to respond to, and there's a whole list of questions that we need to answer. From the technical point of view, I mean, there's the whole issue of what the structure should be like, and we'll tell you a bit more about the development of that. But there are other sorts of questions to do with traffic, how you get people there, how you organise the ticketing. There's a whole safety analysis, the risk analysis that needs to be done, interference to TV and radio. Some people have said, is this going to make such a noise that it's going to be a problem? I mean, it's not going to be going at that speed, so I don't think that is an issue. But the question was asked. And then there's a lot of sort of detailed design issues, like there's a massive spindle there. Can you make a piece of steel that big? What kind of bearings can you have? How long do they last? How can you get at them? How are you going to build it? We've been back to the Port of London Authority to talk about, is it okay to bring barges up with massive pieces of steel, etc. So this has been a really interesting. We've had about a 3-month period to do really a feasibility study, which has been really good fun. So the first bit that we looked at structurally was the whole business of how we support the wheel. So this is, I think the top is the plan, bottom, that's the plan, and that's the elevation. So to start with, if you remember, we had sort of an inclined, just an inclined column tied back by a whole series of radiating cables. The problem with a cable that would be going like that straight down to ground at an angle is it would be providing a horizontal thrust onto the foundation that was supporting it. So we thought about putting in this inclined strut that sort of turns the force around so that we can have the cable coming down vertically. And also we didn't need as many cables as we originally had.
And it took quite a lot of space in Jubilee Gardens, which is where it's anchored, so we wanted to minimise the impact on Jubilee Gardens.
Yeah. And so this design has, this is that inclined member is that member on plan, and then just one going up behind this one here. Whereas, and this one has 2 inclined struts along those positions. And this cruciform member here, this is the element that's the spindle that goes into the hub. this is like this so that we can have a cable here and here, which provides some rotational restraint at the top of the arm, because when wind blows on the wheel, you've got quite a large tendency for the wheel to twist that we need to resist and carry back to ground. And it's much easier to take it back in this arrangement than to try and take it all in torsion on this inclined element. So this is what the current design now looks like. This
On
is
the right,
is,
that is.
yeah.
That's the old one on the left.
Yeah, that's the old one with the inclined kind of A-shaped column with all the radiating ties behind it. And this is the one we've got.
There were about 30 or 35 points of connection to the ground with the first design, and with the new design there's only 3.
So we kind of, at the beginning of this this feasibility study, we kind of opened up the whole discussion again about what the wheel should be like. And you have to go back to the bicycle wheel, which if, say, you have 60 guys, which is quite normal on a bicycle wheel, in fact, then this gives you the thinnest rim, because you've got even support to the rim all the way around its perimeter. But the problem is you can't really build this. I mean, you can't lay it out over the Thames and then hoik it into position. So
Not 500 feet.
not 500 feet. And similarly, I mean, this one on the right just shows what happens if you only have 12 guys or spokes. And what happens is that you're only supporting the rim at much wider centres, so the rim has to span between these points of support. Now, just to remind you that on a bicycle wheel, when you look at it in section, the cables don't go straight from the hub to the rim, they sort of cross over, which gives you bending stiffness out of plane as well. So not only does this have to span sort of in the plane of the wheel under loads like that, but also out of plane, there's more spanning for it. So altogether, the rim is working much harder. I mentioned about construction sequence. In fact, that's turned out to be the most crucial load case for the design of the rim, because you gradually build up. So you've got your arm, and you gradually add the pieces, and you can see how the rim tends to sag under its own weight as you build it up. And the absolute worst case is right at the end here when you want to make your last connection. The scale is exaggerated. In fact, if you had 3 stiff arms, this is showing 2 of them in position, and then another one could be added here. This gives us a much better construction diagram, because you can put a tie in here, which keeps these 2 from having to act as bending elements. They can be just pure compression elements. Whereas here you can see this arm is having to bend to carry the loads. So we realised that there was advantages to adding more arms. Well, we then got into this whole discussion about, what are we talking about here when we're talking about trying to get efficiency? And David threw out this challenge, basically. I said, well, what do you mean by efficiency? And Brendan McNiven, a young Australian engineer in our office, kind of thought about this a lot. He said, I'm not going to be defeated by that sort of question. And so he went back to this physics formula, if you like, that efficiency is output divided by input, and tried to list out what the outputs and inputs are. So the inputs are the materials, and you measure how efficient you are in terms of the weight of the materials and the cost. He's Australian, that's why he talks about dollars. And the cost to the environment. And then in design terms, he meant our design effort. There's time and cost. And the energy to making the material and also to running it is measuring cost and cost to the environment. And what do you have to gain? Well, there's the aesthetics, the wheel itself, and then as part of its environment, and function, which, it has to work. And which you can, you just make sure that it doesn't cost too much. You can carry the right number of people, and everyone's happy with it. And then after the 5 years when we take it down, can we reuse it again or can we sell it? And the external effects. So on its immediate environment, is going to be damaging to the park. It's going to be causing pollution and waste. What good is it for society? And because we were talking about this in the context of how many stiff arms should we have for our wheel. And now this line, which is kind of, this is whether you like it. And this is kind of, Brendan's just sort of saying, well, he picked up that if it's got millions of elements, it's bad, and if it's got virtually no elements, it's good. I mean, that's slightly debatable. But the other thing is that as you have more, if you do have more spokes in it, it's definitely lighter. And if you've got only one, it's ridiculously heavy. And the efficiency, you could say, is to some extent is how much you like it divided by how much weight you put into it. And then within each of these kind of options of how many arms or spokes you've got, there are variations, because you can vary the stiffness of the arms and the pre-stress you put into the spokes and how stiff you make the rim. So it's not a straight line from one to the next, it's not a horizontal line for each of these. There are actually a range of options, which is what this wave line is talking about. But pretty well, it did seem as if the most efficient solution was going to be in this region of either 2 arms with spokes, or 3 arms with spokes, or 4 or 5 arms with spokes. That not having any spokes at all was pretty heavy, and therefore pretty inefficient.
Can you explain what you mean by a spoke?
Oh, right, yes. By a spoke, we're talking about this. Well, if you imagine, you know what a bicycle wheel looks like. That's what I'm talking about. I think we call it a spoke rather than just a tie, because it's pre-stressed, so it can take compression as well as tension. But we've been debating what word we should use, whether it is a spoke or a guy or a tie. Anyway, that's what we're talking about. And we had to keep kind of trying to draw up what it would look like. The slide on the right is kind of, again, exploring this thing about the stiff arm, and whether we could just replace, so this is a 12 spoke option, but 2 of the spokes are actually bending stiff elements. And we've been doing analyses. These are envelope diagrams, which means that they represent the maximum bending moment at that point under all of the load cases, for example. And funnily enough, there's not that much difference in service between the 3 stiff arm option and the 2 stiff arm option. You can see this is 39,000 kilonewton meters, and these are 26, but it's not an order of magnitude bigger. And this is 70,000 kilonewton meters, and this is 65. So in terms of the maximum, it's within the accuracy of our analysis at this stage, really. Which again meant that we had, and in some ways for me that was nice, because I could then go back to David and Julia and say, well, come on, you've got to make some decisions based on what you want it to look like here. You can't just choose on the basis of weight. Drat. Well, these slides just sort of showing some of the things about the rim construction. This is what we put in the current design, in the original design, and we still really like it, which is that the bracing of the rim all goes to a centre point, and we don't have bracing in the face of it. But we've been doing studies on that as well. It's true that if you put bracing in the face, it's a stiffer rim, and it also has torsional stability. This doesn't have much torsional stability, and so the way that we can deal with the torsional stability is at certain points to have cables that actually go to the top part of the triangle, and they can. So if we had it attached there, say every other set of spokes, that we could provide torsional stability between those points. The other thing that we found was an advantage was to have some of these cables coming like this to the edges of the hub. That gives torsional stability to the rim in its plane. Do you want to talk about what some of these images look like? Because
what we were trying to do when we talked about efficiency is we wanted to trim some of the weight out of the structure. We wanted to reduce the depth of the truss. We wanted the least number of ties or guys or spokes. the smallest size sections. We wanted to make it as minimal as possible, but also as visually light as possible with the least number of elements. And it's impossible to have all of those. And so it became a question of balancing them and fine-tuning. So these just look at a number of different options of rim weight, rim depth, as against numbers and arrangement, geometry of spokes or guides.
I mean, the original rim was 12 metres, so now it starts to come down to 10 metres on the left, and then
What we're having to deal with in terms of structure is vertical and lateral load, torsional stiffness of the rim against twisting, and also rotational stiffness at the hub.
I should say we're talking about a hub that's about 10 metres long, 8 to 10 metres long, and close to 3 metres in diameter. A pretty massive lump of steel that's going to be up there. And it's going to have 2 sets of bearings going around it, two rings, which are basically, they're like 2 rims that house between them egg-shaped pieces of very hard steel that act like ball bearings.
I mean, it's got to be absolutely fail-safe. I mean, if anything happens, you've got to, I mean, the 2 systems come into play.
Yeah.
Well, the other thing we discovered is that we could get rid of the stiff arms altogether. They could be taken out.
Yeah. So you need the stiff arms to build it, but if you decide that, okay, they don't have to stay there afterwards, then you can make them the most efficient. You can have the 3 that you need, which so that they're triangulated and they're not carrying the bending. And we can make them as cheap and cheerful as is possible to just carry the forces. And then you take them down and you save them for when you take the wheel down.
This whole process of trying to rationalize, I mean, that's I suppose...
The one on the right, yeah.
The one on the right is, although there's only 60 guys in elevation, in fact, each one of those represents 4. And so visually, it's quite a dense arrangement of cables, although it's obviously very daring on the edge because there's virtually no rim.
It's the one that, particularly I think if you look at it slightly skew, will look the most solid in that region because you'll have all of these crossing over cables very close together. But it will definitely, fade away the most around the edge. And that's part of the thing that we're doing now is looking at more views of all of these options.
We've looked at about 100 different options. And we've settled on the option on the right, which is where we are at the moment, which is, we think, quite an efficient solution and elegant.
These are just 2 views of the capsules. Sorry. Look at the one on the left. So the design of the capsule has been done by mostly by Tom Barker in our firm, the nice young Tom Barker, in our applied technology unit with David and Julia. But there's quite a lot of complicated issues to do with the design of it. I mean, it has to work environmentally. Also, this horizontal floor that stays horizontal as you go around, you have to try and come up with a device that stops people kind of all jumping on one side so that they actually get it going round as you go around. The football hooligan. Well, we're looking at different options of what the structure will be. Basically want it to be a lightweight structure.
They've actually discovered that the orientation of the wheel is actually perfect from the point of view of allowing the solar cells to work in the direction of the solar cells, and then the natural ventilation that will come in at lower level and then come out through the solar cells at the top, which will form louvers.
So what these cells are, they've been developed with BP. They're basically chips, circular blue chips, which can be set into, they could be set into glass actually, but here they'll be probably set into something opaque with an aluminium kind of waffly backing. So, because one thing that happens is if the chips get too hot, they then become less efficient. So this, by allowing the sun to fall on that side and having them arranged so that that they're inclined, and so you get visible light, but facing the north from that side. You also allow air to circulate around it and cool the back of the chips down. And here's some views of what we hope it will be like.
Well, this is the old design, but
Yeah, but that's what its presence would be. Okay, that's it.
We'll be up in the bar, so if you have any questions, let's do it up there in an informal manner. And thanks for coming in and talking. It was great to focus on the one project like that and see how it happened. Thanks.